Problem statement. Water flows steadily through the double elbow shown in this figure. Water flows into the elbow from the top at 5 meters per second and from the left at 15 meters per second. Determine the vertical and horizontal components of the force needed to hold the elbow in place. This problem is asking me about the vertical and horizontal components of the force. So whenever we talk about force, we have to think about the momentum equation. Here we have three pipes, so we cannot apply the equation for one inlet and for one outlet. We have to apply the general equation of momentum. And the general equation of momentum is sum of forces is equal to the sum of elements 1 to n, in this case 3, density I, area I, velocity I is a vector, and times the dot product of the velocity and the unitary vector. Okay, so also we have to draw the control volume. So we have a section 1, section 2, and section 3, and we have the information on the pressures, pressure 1, pressure 2, and pressure 3. So if we draw the control volume, it will be something like this. So I'm drawing the control volume between sections 1, 2, and 3. So that will be my control volume. Now we have to ask ourselves what this water is doing to my control section in 1. So there is a force F1. Here, this water is pushing the control surface with F2. And here we have a force F3. Also, the water is pushing the control surface. We have F3. And then now we have to ask ourselves what the pipe wall is doing to the control volume. So we can assume that the water example is pushing the walls of the elbow to the right, and the walls of the elbow are reacting to the left, right? If that's the case, the elbow walls are reacting to the left. So that will be a reaction in X. And we can assume also that the reaction in the Y direction is uh, in the positive Y direction. So this is X and this is Y. So we can assume that those are the directions. So if the answers are positive, the direction we have assumed is correct. Otherwise, the direction we have assumed is incorrect. But the magnitude will be the same. Only the directions need to be changed. Okay, so let's start with the momentum in the x direction. So we can say, okay, I'm going to first do momentum in the x direction. Okay, so let's see the forces first in the x direction. F1 is going to be positive because it's pointing in the positive x direction. F2 doesn't have a component in x, so we don't need to include that. Now F3 has a component in the x and the y direction. So F3 is going to be negative because the component is pointing in the negative x direction. So it's going to be minus F3 cosine of 40 degrees. The reaction in x is pointing in the negative direction of x, so that's going to be minus Rx. And that will be equal to now the momentum. The momentum in 1 will be density 1, area 1, The velocity vector in 1 is positive 15 because it's pointing in the positive x direction. So it's going to be plus 15. And then the dot product of the velocity and n, okay, so we have velocity is going to the right, and n is always pointing outward. So this is n1, this is going to be n2, and this is going to be n3. So the product of B1 and N1 will be negative because they are in the opposite direction. So this is going to be minus 15. Okay, there is no momentum in pipe 2 because it's only in the y direction. But for pipe 3, we have a momentum in the x direction. Okay, so the velocity, so let's apply the formula again here. So it's going to be plus density 3, area 3. What is going to be the velocity in 3 in the x direction? Velocity of 3 in the x direction. And then it's going to be, the velocity is pointing in this way, this way. So the component will be positive because the component is pointing in the positive x direction. So that's going to be B3, B3 cosine, cosine of 40 degrees, okay, positive. And then the product of velocity 3 times n3 will be positive because n3 and b3 are pointing in the same direction. So that's going to be b3, okay, positive. So it's going to be b3 squared, okay. So from this, the reaction in x um, will be equal to, so Rx can go to the right, so therefore Rx will be F1 minus F3 cosine of 40 degrees. This density 1, area 1 will be, needs to go to the left, so it will be minus, but minus and minus, they will become positive, so it's going to be plus density 1, area 1 times 15, 15 to the square, and minus density 3, area 3, velocity 3 square cosine of 40 degrees. So that will be my first equation. Okay, so let's check if we are doing this correct. So we have F1, okay, we have F3, then we have this, and okay, okay. We know F1 because F1 is going to be pressure 1, area 1. So we know F1, F3 we know. The only thing we are missing is right now velocity 3. And I don't know velocity 3 right now. I can call this equation 1. Okay, so now we have to find velocity 3. How do we find the velocity 3? We can find the velocity 3 um, by continuity, by continuity. And continuity tells me the flow coming in is equal to the flow going out, right? So I can say um, uh, the sum of flow coming in is equal to the sum of flow going out. Okay, so in this case, in pipes 1 and 2, the flow are coming in and 3 is going out. Okay, so we can say Q1 plus Q2 will be equal to Q3. Okay, so Q1 plus Q2 will be equal to Q3. Q1 is equal to velocity 1 times area 1. Q2 is velocity 2 times area 2. And Q3 is equal velocity 3 times area 3. So now we can replace the values here. Okay, so let's see. The velocity 1 is equal to 15. 15. Area 1 is equal to, we have the diameter of 20 centimeters, so it's going to be pi times 0.2 squared divided by 4, plus velocity 2 is 5, and area 2 is, the diameter is 45 centimeters, so it's going to be times pi 0.45 squared divided by 4, and that will be equal to the velocity in 3, which I don't know, and area 3. I know the diameter is 25 centimeters, so it's going to be pi times 0.25 squared divided by 4. So we can cancel pi and 4 in all of them. And then from this, my velocity in 3 will be equal to 25.8 meters per second. Okay, 25.8 meters per second. So I know now the velocity in 3, and I can replace the values in 1. Okay, so now we can say in 1, the reaction in x will be equal to F1, and F1 is equal to pressure 1 times area 1, and the pressure 1 in this case is 250 kilopascal, so it's 250,000 pascals times area 1, and area 1 is pi times 0.2 squared divided by 4 minus F3, the force F3. The force F3 will be pressure times area, and the pressure is 170,000 pascals times the area 3, so it's going to be pi times 0.25 squared divided by 4. Then I have plus, density 1. I have a density, I have a density 1 is equal to 1000 times area 1, and area 1 is equal to pi times 0.2 squared divided by 4 times 15 squared minus density 3 is 1000. Area 3 is going to be pi times 0.25 squared divided by 4 times velocity 3, and the velocity 3 is 25.8 squared cosine 40 degrees. And this will give us a value for the reaction in x of the reaction in x that we get from here is minus 16,500 newtons. This means that the direction that I have assumed is incorrect. So it should be the other way. However, the magnitude will be 16,500. Okay, so only the magnitude, only the direction is changing, but the magnitude is correct. Okay, and we can do the same thing in the y direction. So we already have the reaction in x, and we can do the momentum in the y direction. So the momentum in the y direction then, momentum in the y direction. Okay, so then the momentum in the y direction will be, okay, so let's go back here. From pipe 1, we don't have any forces because all of them are in the x, but now I am talking about the momentum in the y direction. F2. F2 has, there is the force F2 is pointing in the negative y direction, so it's going to be minus F2. Okay, it's going to be minus F2. So here I have a minus F2. And then the reaction in y is pointing in the positive y direction, so it's going to be plus Ry plus Ry. And also I have a component for pipe 3. So I have a F3, and F3 has a component in the negative x direction and in the positive y direction. So that's going to be F3 sine of 40 degrees. So it's going to be plus F3 plus F3 sine of 40 degrees. And then now we are going to have the momentum for pipes 2 and 3, because the momentum in one, the momentum of one in the y direction is 0. Okay, so let's do that. Then that will be equal to, this will be equal to the density 2, area 2, and then we have the velocity in 2. Velocity in 2 is going to be in the negative y direction. So that's going to be minus v2. Now I have the dot product of b2 times n. So let's see that one. b2 is pointing down, but n is always outward, so they have the opposite direction. Therefore, the dot product of b2 and n2 will be negative. So that will be negative. So this is going to be um, minus b2. Now we do the same thing for pipe 3. So we have plus density 3, area 3, and now the velocity. So velocity 3 is going this way, and it has a component in the positive x direction and a component in the negative y direction. So that is going to be b3 sine of 40 degrees minus, right? So it's going to be minus b3 sine of 40 degrees. So the velocity will be minus b3 sine of 40 degrees. And then we have the dot product of the velocity 3 times n. So velocity 3 is pointing this way and n3 is also pointing outwards. So they have the same direction. So the dot product of b3 and n3 will be positive b3. So that will be a positive b3. So therefore I can say, okay, this is going to be b3 positive. Therefore, from here, my reaction in the y direction will be equal to F2 positive minus F3 sine of 40 degrees. Then minus and minus is going to become plus density 2, area 2, velocity 2 square. Then I have a minus density 3, area 3, velocity 3 square times sine of 40 degrees. That will be my reaction in y. Okay, so that will be my reaction in y. Okay, so it's going to be F2 minus F3 sine of 40 is going to be minus density 3, area 3, B3 squared sine of 40 degrees. That's correct. And then I have here plus density 2, area 2, velocity 2 squared. So I know, so we can plug values here. So here I have then let's see here. Then Ry here, Ry will be equal to F2 will be equal to pressure 2 times area 2, and P2 is 30 kilopascals. So that will be 30,000 times area 2, and area 2 will be pi times 0.45 squared divided by 4 minus F3 is pressure 3 times area 3. The pressure 3 is 170,000 pascals times area 3 is pi 0.25 squared divided by 4 uh, times sine of 40 degrees plus density 2, which is 1000. Area 2 is pi 0.45 squared divided by 4 and times velocity 2 squared, and the velocity 2 is 5 squared will be 25 minus density 3 is 1000, area 3 is pi times 0.25 squared divided by 4 times velocity 3, and we found velocity 3 is 25.8. So this is a 25.8 to the square times sine of 40 degrees. So if we plug values here, the reaction in y will be equal to minus 17,600 newtons. Again, I have assumed the incorrect direction for Ry. Okay, but the magnitude of the forces are correct. Only the directions I have assumed are incorrect. So I simply have to flip the directions that I have assumed, right? And that will be the reactions of X and Y. That will be the answer.